Hello, everyone, and welcome to Differentiability and Graphing Derivatives. I think every other teacher in the country does this first, before they do all the rules of differentiation. But I just feel like I've been kind of talking about these things for over a month now, and now this whole section, which is literally nothing but theory, should go a lot smoother because I've been mentioning it ever so briefly on every single lesson. So the formal definition, the derivative of the function f with respect to the variable x is the function f prime whose value is, so you must recognize this. We've talked about it over and over again. Alternately, you are going to see it sometimes, this is the exact same definition. You might see it as f of a. So I'm just going to draw both of them so that they make sense. So here's the one that we're used to doing. I've always said that a derivative is the slope, the formula for the slope at any point along a curve. But in order to do slope, we need 2 points. So the first one is x comma f of x, and then the next one is x plus h comma f of x plus h. And if you could just let h be 0, these would be the same point. But then when you went to go do your slope, f of x plus h minus f of x over x plus h minus x, if you actually let h be 0, if you tried to trick it into giving it be the same point, you'd get h on the bottom, which you can't have. And that's why we learned limits. And hopefully you're sitting there going, yeah, I know all this. That's great. That's the point, is that I've been talking it through the whole time. But I do want you to be familiar with the alternate definition, which is some people call this f of x, or x comma f of x, and then a comma f of a. Instead of doing the whole like x plus h thing, they're just like, okay, you got 1 point, and then you got another point. And so it's going to be f of x for your slope minus f of a over x minus a. And then how would you make these the same point? If you let x be equal to a. But you can't let x be equal to a because you get a 0 in the bottom. And hence the limit again as x approaches a. So, sorry if you're like, why don't you use that one? That one was better. No, I use the x plus h. But they're both good, and they mean the exact same thing. So when you read them in a book, I don't want you to think, oh, a new thing to learn. It's not a new thing. It's just the same thing said differently. All right. Hopefully you remember that in order for there to be a limit, the left-hand limit and the right-hand limit had to agree. And that's what a limit was. This exact same thing is true for derivatives. The left-hand derivative and the right-hand derivative must match. So let's graph this real fast. 0, 0, 1, 1, 2, 4 as it comes in from the left. And then on the right, it's 2x, which looks like that. So right here, the derivative is coming in. It's negative, but it's not as shallow, it's not as steep anymore. And then eventually it's going to be 0. But this one always has a slope of 2. So right here, the derivative is 0 coming in from the left and is 2 coming in from the right. You could actually make a y prime piecewise function 2x and 2, and you would also see it that way. So the derivative at 0 for this one is 0, but the derivative at 0 for the other one is still 2. So it doesn't match. But honestly, the easiest way to just know is if it does anything pointy. A derivative always has to change in a smooth way. It slowly becomes 0 and then slowly becomes negative. It's never going to have anything pointy. Here are the 4 instances where there is no derivative. First, at a corner. That is the official name for this situation. I know I was saying pointy, but the official name is a corner. You must know this name. I'm going to tell you a quick funny story. When I was grading AP, this was one of the questions, and they apparently, not teachers all across the country use the word corner. Here are some of the things that were not accepted. Doink. I'm not kidding. Some kids said at the doink. They did not accept vertex, which actually wasn't bad. They did not accept peak, bounce, node. They did not accept abrupt change of slope. They did not accept not smooth. And they did not accept does not have a slope. All these things, okay? That's because they don't want you to describe it. They want you to know the terminology. Make sure that you know it's a corner, okay? They did not accept apex of 2 segments, spike, kink, sharp turn, sharp point. They want corner. This is called a corner. Now, there is something similar, which is a cusp. So a cusp is when, and we can't actually see this on this, it goes all the way out to 8.2, but a cusp is different. It's where it comes down like a seagull. Are there 2 L's in seagull? I shouldn't have written it. I really don't know. Seagull. Anyway, so it looks like a seagull. And what this is doing is it has a negative slope, right? And that negative slope actually gets really negative. And then all of a sudden, it's an insanely positive slope. So it goes down, it gets more and more and more negative. It's practically like negative, 100 or something. And then all of a sudden, it's positive. That is called a cusp. I'm going to erase the word seagull, probably because I spelled it wrong, but mostly because I don't want you to call it a seagull on the test. Make sure you call it a cusp. A vertical tangent is where the slopes of the secant lines approach either positive or negative infinity. So we're always used to graphing this as 0, 0, 1, 1, -1, -1, and it looks something like this. Okay, this is totally my bad. I have drawn this very lazily for a very long time, and every year I swear I'm going to fix it and I don't. But it actually comes in and it's incredibly steep right there. So steep as to be vertical. For a split second, it's vertical. And that's what they call a vertical tangent. So really quick, I want to show you on your graphing calculator, x to the 1/3, which is the same as the cube root of x. I hit graph. And can you see that? Can you see how steep that is? So, sorry, I've been a little lazy about drawing it all these years. And finally, the 4th one is a point of discontinuity. So this graph is at -1. It's just a y is equal to -1 all the way until we get to 0. And then x is greater than or equal to 0 is going to be 1. Oop, and I can fill that in. So the reason I bring this one up is because if somebody is really algebraic and doesn't like to graph, they might have said, oh, the derivative is 0, the derivative is 0, and they would have thought it did match, but it doesn't. It has to be continuous, so there can't be a derivative where there's not even any continuity. All right, couple things to know. First, a function must be continuous to be differentiable. Number 2, if a function is continuous, that doesn't mean it's differentiable. So this is continuous, not differentiable. This is continuous, not differentiable. But it definitely has to be continuous. A step function doesn't have a derivative at every point. If a function is differentiable, then it is continuous. This is key because sometimes somebody's going to say it's differentiable And it's your job to know that that also means it's continuous. So as soon as somebody says it's differentiable, you can assume it's continuous. That's the important one to know. Differentiable functions are locally linear. That is, a function that is differentiable at a closely resembles its own tangent line very close to a. Meaning, if you have a graph, if I zoom in closely enough on any one point, it should look like a line. You can't even tell that it's a curve. So we're going to do just a fun thing with f of x is equal to the absolute value, which you should all know has a point, and this function, which is a square root, which is going to look just like this, but this one is going to curve out. All right, I've already put the two equations in the calculator. I'm going to hit graph. There's the blue one, and there's the red one right on top of it. So when you first put them in, they look like they're the same. So I'm going to hit my trace button just to make sure that it puts the cursor on there so that when I hit zoom, that's the point at which it'll zoom in on. So zoom, you can either arrow down or you can hit the number 2 and then enter. And I'm going to say enter. And then I'm going to say enter. It'll keep doing the same thing. And then enter. Ooh, you're starting to see it? And then enter. Remember, the blue one is the absolute value. Look at that. Super close up. How close? Look at that window. All right, I'm going from negative 6 thousandths to positive 6 thousandths. Look at that. But the absolute value graph, no matter how much you zoom in, that still has a point. But the other graph, because eventually it curves out, that means eventually I'm going to be able to find a derivative. Okay? So interestingly, I will say, I've taught you how to use, let's quit out of here, Math 8 for n-deriv. You are smarter than your calculator. Are you ready for this? Your calculator does not know how to find the derivative of the absolute value of x at 0. At 0, it's going to say that the derivative is 0, but it's not. The answer is the derivative does not exist. The reason your calculator can't properly do the absolute value is because when your calculator does a derivative, instead of using this point, x comma f of x, and then its second point, x plus h, comma f of x plus h, your calculator instead uses the point x minus h, comma f of x plus h. So it's not taking a limit like we are. It's just saying, I'm just going to use two really close points. And in order to even it out, it uses a point to the left of the given point and a point to the right of the given point. But because it does it symmetrically, it's going to get a slope equal to 0. So it is the only thing on your calculator that I know to be wrong about it. It says that the derivative is 0, but it is not. So you are smarter than your calculator. All right, this, in my opinion, is a super fun section. These are like little puzzles. So we're going to make this graph. So it goes to the left 2 and up 1. It's a basic parabola. So 1, 1, 2, 4. 1, 1, 2, 4. We have parabola. Now we're going to make a graph of the derivative. So how can we graph the derivative? It doesn't have to be exact. It's just a general shape, because we could actually find the derivative at all these points, but just a general shape of it. So I know that if x is 2, right there, the derivative is 0. So this is going to be a point on my graph. Before that, I know the slope is negative. It's really negative, and then it's a little less negative, and then it's really less negative. Now, I don't need to actually plot those points. I can just go like that. And after that, the derivative becomes positive, more positive, and then an even greater positive number. So I'm just going to go like that. Do I know that I have that slope exactly right? No, in fact, I know I don't. I know that the derivative is going to be 2x plus or minus something, but it doesn't really matter because I just want you to have a general shape of what it's going to look like. And sure enough, it goes from a parabola to a line. Here I go, plugging my battery in for the day. All right, do the next one. Graph sine of x. And this will really help you see it too. I know we've already done this back when we did trig functions, but it'll help you understand the concept. So 0, 0, 1, back to 0. You don't need me. I assume you're doing it on your own. So if somebody asked you to graph the derivative, you could say, well, I know that at pi halves, the derivative is 0. So at pi halves, it's 0. I know at 3 pi halves, it's 0. At negative pi halves, it's 0. And the derivative, remember derivative is slope, at negative 3 pi halves, the slope is 0. And what is the slope between pi halves and 3 pi halves? The slope is negative. So I need to plot all negative numbers. But it's right here that it's the biggest negative number compared to there, right? That's its steepest slope, right in the middle there. So right in the middle, I'm going to go as steep as I'm going to be. And other than that, it's not that steep. And that is how you can graph a derivative. And of course, what is that? That's cosine of x, which we knew. So of course, I have to give you one now that you don't know. Graph a positive cubic function through the point 1, 0, having a maximum at 2, 4, and a minimum at 6, 1. So I'm going to come up, maximum, minimum. All right, so here's one that you don't even know the function, let alone its derivative. Can we make the graph? Yes. You know on this derivative graph, when x is equal to 2, the derivative is 0. And when x is equal to 6, the derivative is 0. And what is it in between there? Negatives. So these all have to be negatives. But as soon as you get to 6, the slope becomes positive. And as soon as you get before 2, the slope is positive. Did I necessarily make that the right parabola? No, but you definitely should have a sense of what it looks like, okay? Last one. Ooh, now we're going to try it backwards. All right. F prime of x is 2 for x is, by the way, you should really try this one on your own and turn it off and see if you can figure it out. It's a puzzle. It's kind of fun. So greater than 1, I'm going to be up here at 2. It looks like that. For less than 1, I'm down here at negative 1. All right. Given that f of 0 is equal to 0, so I have to go through this point, and I have to make my graph continuous. So I'm looking for something that has a derivative of negative 1 all the way through here. So a slope of negative 1 would look like that. Oh, but all the way to, it has that slope all the way. So I have to go through that point, but I'm not going to stop there because it has a slope all the way down to there. And now from 1 over, it has a slope of 2. This is the original function f of x. This is its derivative. It has a derivative of 2 for everything greater than 1. It has a derivative of negative 1 for less than 1. And see how neither one of these are equal? That's because it has no derivative at x is equal to 1. That's why these are both open. See how it's all coming together? And I went through that point, f of 0 is equal to 0, and I made it continuous. So fun little puzzly section here, and I hope that it all made sense. Have a great day.